Okay, welcome to the first, it's the first, right? The first IAP colloquium for 2026. So I use this opportunity to send my best wishes to everyone I haven't done to at the moment. It's my pleasure to introduce Pierre Auclair, who has been working for many years in a very weird topic, cosmic strings, namely, and many other things. Pierre had a PhD in 2021, if I'm not mistaken, under the direction of Danny Stier, whom we know quite well at APC, and Chiara Caprini. He's been working on a lot of things, on cosmic strings, first-order phase transition, primordial black hole formation, with a lot of other people as well, and of course gravitational waves, which are coming from all these things. And he's been working with around here as well, with Vincent Venin, whom we also know quite well, and Mark Heinmarsh in particular. And I think I'm not missing anyone. Oh, yeah. And he spent quite some time in Belgium, in Louvain, with Christophe Ringeval. He's also quite well known here, also in cosmic string. But then he went into inflation, stochastic inflation, and all these kind of things. But I think today he will restrict attention. So he's located in, the most important point, of course, he was hired by CNRS last year. And so he just arrived at the end of 2025. And he's now, and you can find him if you want, on the second floor.
Yeah, I put the office number there.
Office number 275.
I don't know if it's large enough, but you can come anytime to ask questions or just for coffee or anything.
And so today we'll restrict attention to cosmic strings and gravitational waves. Okay, the floor.
Yeah, thank you, Patrick. So it's a great pleasure to be here at IAP, and I'm very happy to spend the following years here at IAP. I was even registered for 1 century, I think, for the canteen. So I'm bound to stay here for a long time. So I will be talking about cosmic strings and also in the context of a decade of gravitational wave observations. I was also asked to do something very pedagogical, so I will try things. This is my first time trying an experiment on the table. Yeah, we will see if that works or not. So just to give you an overview of what I want to talk about. So I guess everyone is familiar with this picture. We are on the right-hand side. And what I'm interested in basically are the first few seconds, the primordial universe. And in particular, what I'm interested in is what happens if you have phase transitions in the early universe. Think about grand unification theory, electroweak phase transition, QCD phase transitions, these types of things. And during this phase transition, you may have remnants at the end, which are called cosmic strings, which I will introduce, that were generated basically at the very left part of my plot, and that survive for a very long time. So I will spend the first part of my talk to explain what is a cosmic strings, how do they behave, how do they organize themselves in networks, and how do you compute basically their signatures. So then all these objects throughout the history of the universe, they remain here and they emit a lot of signatures. For us, we will be interested in gravitational waves. And you also need to estimate basically those signatures. So this will be the second part, followed by how do we observe those signatures. So basically in terms of gravitational waves, we will be interested in here in pulsar timing arrays, LISA, also a space-based gravitational wave detector, and also ground-based detectors like LIGO, Virgo, and in the future, Einstein telescope. So throughout this presentation, I will try to give you a simple, from beginning to end explanation, but I will keep hiding things from you that I will put in a small box. So you will find a small box on the bottom right corner when there's something I'm not telling you. And at the end, we will open the box and see what's inside. And I think what's inside this box is basically everything that's interesting to do right now on cosmic strings. And I will explain one of the items I'm selecting right now and I'm working on so that we can start with some new ideas for projects. So what is a cosmic strings? So I will have to talk about cosmological defects in the context of cosmology. So as you are all very well aware, the beginning, the universe was very hot. And if you think about the Higgs model, for instance, you may have some phase transitions and spontaneous symmetry breaking. So just to give an idea, you have on the right-hand side the potential that I will put like schematically. This is my barrier of the potential. I have a real scalar field. It can be either minus or plus here. And I'm just talking about one dimension. So this is where the experiment comes in. So imagine here you have your one-dimensional lines. So this is like space, like this. This is minus infinity, plus infinity. So your universe is cooling down, and eventually it wants to reach a state with the lowest energy possible. So basically what it can do, you have all your space either falling into the minus side or the plus side. This is the ideal situation, but it's not necessarily the case. Because you have something which is in principle causally disconnected, you may have like minus infinity that choose to stay on the minus side. Your plus infinity is stuck on the plus side. And in the middle, you have your basically state doing some crazy things. But at the end, what happens is that you want to reach the lowest energy state possible. You want to minimize gradients, and you want your field to stay in the lowest energy state. So basically, you try to strengthen it. But there's no way you can have something where everything sits on the same side. You have a topological invariant that tells you that basically you cannot reach the lowest energy state. Instead, you reach another state which has a little bit more energy, but that is stable, because you would need to take half of your universe and jump it over your barrier. So eventually, that's what's happening. So the simplest topological defect you can imagine is called a kink. So you can have this nice formula with a hyperbolic tangent, and it looks something like this. So this is my one-dimensional line. Minus infinity is minus, plus infinity is plus, and you have a transition in between, and you can compute its shape depending on your field. And what happens is that at the middle, you have some energy. You have something that's some energy localized in the middle. It has a certain width, but it has some structure. It has some physical meaning. So this is the simplest example you can imagine. So it stems from spontaneous symmetry breaking. You have an idea of topological stability, which gives its name. It's impossible to continuously transform this system into a system without a defect. You have some topological invariant behind it. And those structures, they have some localized energy, and hence they are interesting for doing physics. Now, the next system, going to cosmic strings. So I'm not talking about lines now, I'm talking about circles. So let me just try to close this to have a loop. So I'm always showing the right-hand plot with a Mexican hat potential. So you have potential with U1 symmetry. And now your vacuum manifold is not just plus or minus, it can be any angle. So now you do the same trick as before. You look at some region of space, let's say a circle, and you look at what's the state it takes. So you can have something very trivial where everything sits basically the same side. And as you reach the minimum energy state, you reach a trivial state where you have basically everything, all your air going in the same direction. But you can do some, because of the same argument as before, you can have something that entangles around your Mexican hat potential, and you can do anything you want. You will not be able to basically unwrap it. So think about a vortex, or basically me, for instance, with my hair. I could try to brush my hair as much as I want. I will not remove this vortex that I have in the front. So it's basically the same thing, and it has a bit more structure. You can imagine basically doing one full circle around it. Then you can do two, you can do more. And all these states are not identical. They represent different equivalence classes. And those classes, you can represent them mathematically with what's called the fundamental group, pi1. And this is just some mathematical way of saying that you want to wrap a circle here on your vacuum manifold. And it's how many ways you have to wrap it around your manifold. So here you see that you have Z, because you can wrap it like positively in this side. You can do it as many times as you want. So you can have positive integers, and you can have also negative integers. And the thing is, we expect strings to be formed in most models of spontaneous symmetry breaking if you believe in grain unification theories. So this was the study that I'm citing in 2003, where I think some of Jeannot was at IAP at the time. I'm not sure. No, some of the members were at IAP. Yeah, Patrick will correct me. But basically, in most cases that are compatible with cosmology, you expect cosmic string to appear. So those are a natural object to expect to study if you want to look into grain unification theory, for instance. So in practice, what does it look like? So here I've taken a picture, and actually I'm cheating a bit because this is not really a cosmic strings. It's a topological defect in a liquid crystal. But the idea is the same. It's something that you can have in other systems. Topologicals are quite ubiquitous. So here I will be taking an explicit example, which is the abelian Higgs model. It's a local UN symmetry, so you have a complex scalar field and a gauge field. And you can also try to see if you have some profile for a straight string. So you can do it. And it looks something like this. So here I'm taking radial, basically, coordinates. So I have a straight string like this, and I'm looking at the radius. So I see that at the middle, my field is not in the what you would expect for the vacuum expectation value. It's sitting on top of the Mexican hat potential, and it has some energy. And at infinity, and actually quite fast, the scale that's roughly the mass of the scalar, basically, it reaches like the expectation value. So it's really something that's localized here. And you can also do the same thing to look at where the gauge field is localized, but I will not talk about this right now. So the properties you see are the following. You have some energy that is confined in the small region, the scale of the mass of the scalar. And you can say also that it has some energy per unit length, a tension, basically the size of the energy scales in your phase transition. And here, for the abelian Higgs model, you have no long-range interaction. And here, I put a box because I'm hiding stuff, and I will come back to that later. So something natural you can do with that, with these properties, is to try to model it mathematically. Solving the abelian Higgs model is quite complicated. You need to solve it on a lattice, and I don't want to do that. So I'm taking the Nambu-Goto approximation, something that people in string theory are familiar with. It's basically a very simple action that you see here, with tau being a time-like coordinate and sigma the coordinate along the string. And the determinant is just a fancy way of saying that you want to minimize the area that is swept by the string in space-time. And in front, you have the mass per unit length mu that characterizes completely your string. So you forget everything about the microphysics. You assume that it's infinitely thin. And this action allows you to study how it behaves. Yeah. I guess the value of mu is linked to the parameters of the Lagrangian, so the eta that you see. And I think you could, in principle, this is an effective action, and you could, in principle, include other contributions that come from the curvature of the string. But that's like the first order effective action, if you want. And I think in the textbooks, you can find how to derive it from the Lagrangian. So you forget everything about the microphysics. You have one parameter, the linear density, and you can relate it by a rule of thumb, basically, to the energy scale that you want. So if you say grain unification theory, you have symmetry breaking at this scale, then you expect linear density to be of the order 10 to the minus 6, and this is a dimensional parameter, basically. And if you go to lower energy densities, it means later in time, so lower energy. So I can solve it in flat space-time. So here you have an actual loop, a very simple loop that's oscillating. So if you solve it in flat space-time, it's just like a guitar string. You have a wave equation, and you have two modes, one left-moving mode and one right-moving mode with some properties. And you see, written like this, that if you have a closed loop, it's periodic around the space-like coordinate. So it means it's also periodic along the time-like coordinate. And so this means that it oscillates with a certain period that's proportional to its length. And by doing this oscillation, if you are familiar with gravitational wave, it's kind of obvious that it will emit gravitational waves. It has non-zero quadrupolar moment. And then you have features on those cosmic strings. One of them is kinks. So basically your string is a continuous object, but its tangent vector is not necessarily continuous. And you have some sharp features like these that propagate either left or right. And those kinks emit gravitational waves, and they basically continuously emit gravitational waves as they propagate. Those kinks, if you have a left kink and a right kink that collide, they emit gravitational waves isotropically. And then you have cusps. So to see cusp, I'm just stopping the movie from before. And you see here that you have some pinches on the string. Those parts are transient object that we call cusp, where basically you have the tip of the cusp that goes instantaneously at the speed of light. It's just transient thing that happens. If you were to have a proper field theory simulation, it would not be exactly going down the speed of light, but slightly below. But still, it's a very extreme event that generically happen on cosmic string loops, and that emit gravitational wave in a beam that you can also compute. So that's basically how one loop behaves. And then we can put all this equation on a big simulation that I will show you now. And this, by the way, is the code of François Boucher, Christophe Ringeval, and also Bennett. I forgot his first name. Okay. But one of the first codes of network evolution. So we can look a bit at what it looks like. So basically, this is the initial mesh, the initial network. So basically, how it works is exactly what I did, but bigger. You throw random phases everywhere in your system. You take loops everywhere, and you see whether you have winding number in some ways, in some parts. And then you draw those cosmic strings, and then you let them evolve using the Nambu-Goto action. So first, it's a bit, there's things everywhere, but yes, and just to keep in mind that here you have the Hubble scale that gets larger and larger as you let it evolve. So you see there's a lot of things. You have infinite strings that are in white. And as you zoom in, I don't know if you can see everything, but you have some red and yellow objects that are loops, basically, that form, that oscillate. And you see more and more structure here. And that fragment and produce a lot of tiny loops. And you see that evolve like this. So I will not show the entire movie. But basically, you can use those simulations to get some hints about how this network evolves and also compare it with theoretical modeling. So to come back to my slide, so this is the snapshot of this thing. There are several things that we can say. And the most important one is that you have an attractor solution that seems to emerge whatever the initial condition you put in your simulation. And that's called the scaling solution. And that's a generic property that we find in those Nambu-Goto simulations. The fact that you have this attractor solution that's characterized by the finite number of length scale, typically the length scale between the infinite strings, the length scale of typical correlation along the network, or the length scale that characterizes the energy contained in the network. And all those length scales are proportional to the Hubble radius, or to say differently, to the cosmic time. And this is a big help for analytical modeling. So the consequences are huge. You can forget about the initial conditions. You have just one attractor solution. That's very nice. It also means that since your network follows these laws, it survives for an infinite number of time. And actually, you can show that the energy density is always the same as the background. So in radiation era, it will decay like radiation, and in matter era, it will decay like matter. So it's always staying. You cannot remove it unless you add some other things. And the fact that you have proportionality between length and time means that you can solve equations faster by using some clever enzymes. So it's also very used in our community. So that's it for, no, I still have something else. So from this picture, we see that you have a few infinite strings, and then you have a lot of dots inside. And those dots are loops, and loops are the objects that produce gravitational waves. So what we are interested in eventually is to estimate the loop distribution. And you can do that by a simple model of a continuity equation that's made of a few parts. So basically, what we do is we separate infinite strings. We study them separately. We study them with the simulations. And then we use those results to make a continuity equation, assuming that loops are produced, and then they just emit gravitational waves forever until they decay. And so here, I'm just going very fast here. So you have on the right-hand side what's called the loop production function. It's describing the interaction between the infinite strings and your loops. And it can be of various shapes that I will not discuss too much today. And also, you need a decay rate. So we know that loops, they emit gravitational waves. So that's one way they decay. But they also lose energy to the fields that constitute the string. So that's something that's known and that we try to incorporate in there. But still, there's still active work on these topics right now. And what it looks like, so this is one of the models in consideration by Blanco Pilado and his collaborator that I will call BOSS model here. What it looks like is basically, so here everything is scaled. So the fact that you have scaling means that you can write all the length scale divided by time, and the number density decays like t to the minus 4. So you can rewrite everything, and this is all the information you need for the loop density. So what you have is a power law, basically, and then you have a typical scale where your power law bends, and this is the typical gravitational wave scale. And it is set by the tension of the string. So that's the general shape that you look for in loop population models. Okay, so that was a very long introduction on cosmic strings, and I'm still continuing because now I want to discuss the signatures of cosmic strings. And one of the first signatures you can think of is what happens if I look at a cosmic string. So here I'm also doing a small experiment. If that is not explicit enough. So if you look at the metric around a straight string, the metric looks flat, but it's actually not. If you look at the angle, you have a deficit angle. The fact that your angle does not go from 0 to 2 pi, but some value a bit smaller. So you have this deficit angle here. And what happens is that even though you have a flat metric, you still bend light. And the reason is that if in this case, you have this flat metric. So if I'm an observer here, light rays propagate like straight. But if I remove an angle, what I obtain here is still like flat, but it's a cone. And those light rays that appeared straight in my flat metric are not flat anymore. They are bent. And you see that my observer observes two sources, basically, with a separation angle here that actually direct to the same source. So what happens here is that because you have this kind of metric, the observer would see the same source twice behind the string, and it would be actually like kind of a mirror symmetry. So that's the typical thing that you would see if you were to look at a cosmic string. You would see some mirror symmetry behind it. So typically, this is CSL1 that was observed by the Hubble Space Telescope in 2003. And it was thought to be precisely one of those lensed objects. It turned out eventually that it was actually not, just two very similar galaxies interacting with each other with the same chemistry and everything. But still, I mean, that's the kind of thing you could look for in the sky, and it would direct to a cosmic string. And eventually, you can also look for line discontinuities, for instance, in the CMB. If you have, you can also look for anisotropies in the 21 centimeter band, and also look for these characteristic lensing patterns. But what I'm interested in is mostly gravitational waves. So as I said previously, those cosmic strings, they are quite extreme objects. They have very localized energy and they move at relativistic speed. And so they emit gravitational waves. And I will just use the example of the cusp that I presented before. And we actually know what the waveform looks like for a cusp. So here, the minus q here is just because you can use the same formula for different features. Here, q is is 4/3. So what you have basically is an amplitude that's growing as the length of your string grows. It's also growing when the tension grows. And it's basically a power law in terms of frequency. And the signal you could look for instance, in LISA would be a signal roughly of this shape on the time scale of a few hours for LISA, but on much smaller time scale, for instance, in ground-based detectors. So that's if you're looking for individual bursts, but eventually all those bursts that you do not detect, they accumulate to form an uncorrelated sum, basically, that's called a stochastic background. That's basically a noise, but that would be correlated in all your detectors. So by correlating different detectors, so different ground-based detectors, for instance, or in case of LISA, different arms, basically, you can look for this uncorrelated sum. And I'm not showing this, the integral here, but basically, you have to imagine that it's an integral over all your past Lycon, because there's cosmic strings throughout the history of the universe that takes into account the population of those cosmic strings that evolves with time. And also the fact that some of these bursts are not directed towards you. So you also need to account for the fact that there's a certain beam and you only see them if the beam is directed towards you. So that's with all those elements, you could write yourself the integral. So that's why I'm not showing it. So, okay, so what about observations? So I guess I don't have to present LIGO, Virgo, Cagra to this audience, but this is a plot of, this is just the pictures of LIGO, the two LIGOs and Virgo. But we have not detected cosmic strings in O1, O2, nor O3. And this is, for instance, a sketch of all the candidate events that we have. So that we had in O3. So of course, you have some false positive, false positives. And this is how we represent them. And that's basically some fancy way to say that all the candidates that we have are basically compatible with false positives. We don't have a candidate that's so strong that it would be weird to have it. I mean, that it would be, that it would be a real event. And from this observation, you can still try to see, to compute bounds. So the idea here, so here you see the detection efficiency. You inject signals in your detectors, phase signals, and you see how well your detector is about to reconstruct them. So this shows you that the detector is quite good at reconstructing cusps, basically, but still below a certain amplitude, there's no way you can reconstruct them. And basically, you can compute from a certain model the rate of events you expect in your detector. And if this rate is too high, then that we did not detect anything, then it excludes the model. That's basically the idea. So that's one way to do it, but it's not very competitive with respect to the stochastic background. And this is what the stochastic background would look like in two of the most used model of cosmic strings. So there's a lot to unpack here. So basically, those curves here are the detection curves of LDK. So here and there. And those two are two models. On the left-hand side is the BOS model that I presented before. And on the right-hand side is a model by Christophe Francheval and collaborators. So they are quite different, but I will not explain now what the difference is. The idea that you should look is that it's mostly a plateau at high frequency. So that's why it's so it's efficient to look for it in ground-based detectors. And the fact that it's a plateau is precisely because they emit gravitational waves throughout the history of the universe. So that's why it's ranging all the frequencies. And here you see that you can basically, in this case, constrain the tension to be about 10⁻⁷, 10⁻⁸, so which is compatible with CMB. And on the right-hand side, actually, the constraints are very stringent and basically rule out cosmic strings down to g mu 10 to the minus 15. So you see here that there's some kind of tension in terms of population modeling. Yes, so it's actually quite small, but you see O3 is the dashed dotted is O3 power law integrated curve, and then you have design and A plus sensitivities. So that's why they're lower. And this is what the constraint look like. So forget about the x-axis; it's not very important. But basically, the idea is that in one model you can constrain the tension to be 10 to the minus 8, which is not a very stringent bound. And on the other side, you basically kill all the values of the string tension. So the results are quite different. But I can talk about it at the end if you want. And another way to look for them with gravitational wave is to use pulsar timing arrays. So they are made quite the news 2 years ago, maybe nearly 3 years ago. So basically, they are radio telescopes observing pulsars. So pulsars are basically neutron stars that rotate very, very quickly on the order of 10 to 100 milliseconds. They have strong magnetic fields, so they emit a jet that I think you are more familiar than I am. But basically, this jet is not on the rotation axis of the star. So basically, from a distant observer, you see nothing, and then at some point the jet is directed toward you. So you see pulses basically every tenths or hundreds milliseconds. And so those precise clocks, they keep emitting photons towards you, and those photons, they feel gravitational waves passing. And so because they are so precise clocks, the fact that the photon is affected by the gravitational wave, you can actually detect it on Earth. And it causes basically either a delay or some residual in the timing basically of your photons. And by correlating different pulsars, you can basically disambiguate noise and get really the remaining stochastic background. And in 2023, a lot of experiments throughout the globe in North America, Nanograv, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, Chinese Pulsar Timing Array, and Indian Pulsar Timing Array all found that there was something in the data and that there was indeed a stochastic background that might have been detected. And this is very, very interesting for doing science, I think. So you see here on the left-hand side is the base factor reported by Nanograv, the North American experiment, and against the null hypothesis that it is basically the stochastic background from the merger of supermassive black holes. Because we expect supermassive black holes to be there and to contribute. It's still a difficult source to model, but it's like kind of the null hypothesis. And what you see here being called stable C basically to super here, those are different kinds of cosmic string model. So stable cosmic strings with cusp, kinks, metastable strings, superstrings. And some of these models actually are favored by the data compared to the supermassive black hole hypothesis. And if you take the joint constraint, new physics plus supermassive black hole binaries, even in these cases, some of these models stay compatible with the data or even favored a tiny bit. Yeah. So I removed those slides, but basically what you look for is called the helix Downs curve. So it's saying that if you have a pulsar here and another one here, and you have an observer here, and let's say you have a stochastic background of gravitational wave that's like surrounding all of you, basically you can show that if you correlate this pulsar to this pulsar, the amount of correlation depends only on this angle here. And it's called the helix and Downs curve. It's a nice computation to make. So that's why I put the time delay before, because and I think it would be like, never remember. And basically, it looks something like this. And it's actually not a perfect cosine. It's actually going a bit, it's a bit asymmetric, something like this, if I'm not mistaken. And you basically correlate all the different pairs of pulsars, and you try to see if it matches this kind of curve. Yeah. So headings and downs. Okay. And you see here the power spectrum that's been reconstructed on the right-hand side by the European pulsar timing array. And you see the two different models, the bus model that I had on the left before and the right model. And they are kind of both compatible with the data. So there's still room to say things about cosmic strings with pulsar timing arrays. And then you can also talk about the future. So I will go briefly here. But if we have the Einstein telescope in the near future, we can hope to basically constrain those two models to very low tensions. And you see that you would basically be able to go down to like 10 to the minus 16, 17. So this is like 6 orders of magnitude better than the pulsar timing arrays. So it means that if in pulsar timing arrays it is a cosmic string signal, we would be able to disambiguate it completely with Einstein telescope. And this is the rate of burst that you would see in Einstein telescope, assuming that the pulsar timing array signal is indeed a cosmic strings. And what it means is that, yeah, in some models, you would basically expect to see individual bursts in your detector. So you would be able to find some individual sources. Yeah, I'll not go too much into the details. And then there's also LISA that I talked about in the beginning. So it's a space-bound gravitational wave detector, 3 satellites separated by 1.5 million kilometers. And then you can look for a stochastic background by basically combining the signals in the different arms. So it effectively looks like different detectors, and you can use that to see whether to disambiguate noise from the stochastic background. And in all those cases, you see that with an SNR of more than 10 or 100, you can also reach similar constraint as the Einstein telescope. So both of these experiments would be very good to either rule out completely cosmic strings or to have a detection. So this would be a comparison between the two models here that are compatible at the low frequency part, but not compatible at the high frequency part. And this is also something that might be interesting. So if we have indeed cosmic strings in the universe, and we look for them in LISA, we would actually be able to find probably individual bursts. And the fact that your cosmic string is an oscillating object would also be able to see it repeating in the sky. And that's something that I've been working on a tiny bit. And what's interesting is that your detector basically is moving in your solar system. So if you have a repeating signal on the order of a few months, for instance, then you would see its SNR change in your detector. And this trajectory would be a signal that helps you identify the localization of your source. So that's something that I've been interested in. Okay, so far I've tried to draw a consistent picture of cosmic strings, how they form, how they behave, what's their signature, and how to look for them. And every time there are things that I hid under the carpet. And now is the time to open this box and see exactly what remains to be studied. Okay, so those are all the different things I said. So first, and Patrick, I think, saw that before, I talked about local strings, the abelian Higgs model. But these local strings, they are very nice because I said that they have no long-range interactions. But it's not the only thing that's possible. If you have global strings, so no gauge bosons, actually you can show that your scalar field extends on very large scales, and you do have long-range interactions. And why is that interesting? It's because it's what happened with axionic strings, for instance. So if you have, for the axion scenarios, basically you have the breaking of your symmetry, you have strings forming and then decaying. And the dynamics of your network will give you basically the properties of your abundance of axions and their masses. And that's something that's studied. For instance, here is a simulation by Amelia Drew, who's applying to CNRS this year with IAP. So you can support our application, for instance. And what you see here in gray are cosmic strings in a simulation, and all the colors basically are your massless scalar field, massless radiation that would correspond to the axions later. So that's one thing that's very active at the moment. Another possibility that I hid under the carpet is that you don't have just a scalar field and a gauge boson in the universe. You have other fields, and if they are coupled to your strings, then you can have currents on your strings. You can have other fields that condense on your string and propagate, and sometimes even be superconducting. So I don't have a movie for this one, but here is a snapshot from a simulation by Jose Correa, who was in Finland and I think moved to Norway. And all the colors you see are basically telling you that you have fields that condense on the string and then propagate. So it gives you additional degrees of freedom that you have to model. And Patrick here is an expert on this topic, and you can ask any question about that. And then even in the idealized scenarios that I presented, with local strings with no overfield, there's still some room for improvement. So here you see a simulation of an abelian Higgs simulation. So in principle, no long-range interaction, you don't have overfields, but still the phenomenology is a bit different from what I presented. So here is a field theory simulation on a lattice. What you see is that, maybe I can relaunch it. Yeah. Yes. So you start with roughly the same type of initial conditions. You let it evolve. It seems to reach a scaling where basically the length scale gets larger and larger. But you don't see loops in those objects. It looks like everything is decaying to particles. You don't have small loops emitting gravitational waves and everything. So that's a huge controversy in the cosmic string community. This difference between field theory and Nambu-Goto strings that are idealized. Is it the lattice that is not with enough resolution, or is the effective action not good enough? So that's an active field. And it's been like tackled. So this is a comparison between a Nambu-Goto string, that's the sharp thing, and the field theory simulation. You see that when you have sharp features, they start to disagree with each other. And those groups, they've been doing that for more than 25 years and still exploring the discrepancies between them. And then what I'm interested in, and I think I have 5 minutes to discuss about it, is basically all the other part. The fact that maybe the attractor solution is not really an attractor, and the way we model the loop production function is not very good, or the fact that we assume that all those loops, they oscillate forever without intersecting is also not a good approximation. So one of my topic has been working on fragmentation those past 2 years. And it's not a new idea. So this is a simulation, and actually I don't have the movie here, sorry for that, from 2011, where Tanmay Vachaspati and Kopi, I forgot her first name, studied artificial loops with no angular momentum and see how they evolve. And mostly those loops fragment until they reach like some stable square configurations. And you see that they fragment quite a lot. So, oh yeah, I can do that. So you see basically that they start with a lot of fragment and they decay until by quite a large amount. Like at the end, they have like more than 100,000 loops. So yeah, quite a lot of fragmentation. And the question is, so this is artificial loops. What happens in the network where you have realistic loops? That's a big question. This is in Minkowski, where in principle there exists oscillating solution, but in an expanding background, in principle, they are not oscillating. You have some Hubble damping, so that might also play a role. Is there some typical fragmentation scale that appears, and is it scaling with time? Those are questions that I'm interested in. And just to show some of the things that, two things that I'm very interested about. So this is an equation that's actually not new. It's from 1998. It was by Ed Copeland, Tom Peeble, and Danny Steer, my PhD supervisor. And it's precisely trying to include those self-interactions, the fact that when loops collide, they actually can merge into larger loops, and they can also fragment. So this is a very complicated and mathematical way to say it, but basically the idea is that, yes, this one. This is the continuity equation we saw before. This is to say that you have two loops that collided to form a larger loop, and B is telling you that you have fragmentation. And they also made assumptions about what the fragmentation should look like based on arguments about random walks, Brownian motion. And they say that basically you should expect a power law of the order of -3/2. So I just want you to keep in mind somewhere this -3/2 because it's very interesting. And what I find amazing is that at the end of my PhD supervisor's PhD thesis, this is the very last paragraph. And what I saw was, due to the complicated nature of the rate equation, we have been unable to verify our predictions by a numerical solution. And that has been the challenge I've been trying to do these past 2 years, basically. So continuing on this project. So now, when I was in Belgium, I was in the group of Christophe Rangeval running those simulations, and we tried to find new ways to analyze those simulations in order to say something about fragmentation and collisions. And the thing is, in those simulations, loops are just objects, and fragmentation and collision are already tracked in the software. You just need to keep a log of all of them. And we try to store and use this information. And it's actually something we did. And what I have now on my laptop is basically a registry of all the fragmentation and collision that happen. So we have basically a registry of loop 1 and loop 2 collided to form another loop. And this loop fragmented into two smaller loops, and I have their size, the time of their exchange, the order of their energy, and everything. And this is just using a code that's been around from the 90s. You don't have to do much to obtain those results. But you can do some nice things. And this is, for instance, the family tree of one loop. So the idea is that the size, the area of one circle is the length of one loop, and the color is time. So you start from the darker part, and you see that you have fragmentations appearing everywhere until you reach lighter colors, which are the end states. And what you see is that you have a loop that starts here, fragments. Then you have fragmentation, you have recollisions. You see that it's not like you have some loops in your graph, but at the end, your end state is basically a bunch of very small loops. Your big loop fragmented into a very large population. And this is not something particular. I can do it for other trees, like these, for instance. And I have many more trees that I could show you if you wanted. I can look at what's happening in my simulation, and what's very apparent is that throughout the simulation, it's not some transient effect at the beginning. I have fragmentation throughout the simulation, and the fragmentations tend to be the dominant factor. It looks like I can neglect collisions, and it makes sense. I mean, it's far unlikely in the void to find a partner to collide with. And if I look at the distribution of the children loops, what I find is this shape that seems to be very compatible with the -3/2 that was hypothesized in the 90s. So it looks like I can build a model based on these elements. And that's what I tried to do in a paper recently. So I don't have much time. But basically, I'm taking this old model that was intractable numerically, and I add some assumptions based on my simulations. I neglect the collisions. I neglect also the superable loops. I'm just interested in subbable loops because I want to do gravitational waves. And I can build an ansatz for the fragmentation because it looks like this ansatz from the 90s makes sense. And I obtain this much simpler equation that I can solve actually with different means. One way to solve it that I find neat, because it's very stupid, is to do actually cascades. So imagine you have basically an atom, you know its typical decay time, because this is what we have here. I can just integrate the fragmentation, the probability to fragment, have a typical decay time. I can compute the probability to still be alive. And as you know, if you have the cumulative probability density, you can throw random numbers with this same probability. So you just have to invert it, and it gives you can throw random numbers, and you can throw basically the one realization of your cascade. And you can do the same thing for the size of the fragmented loops. And you can build iteratively, start with initial loops and see what the cascades look like. And you can, if you do that just a few times, it doesn't give you a lot of things, but it's very efficient. And you can actually go to very large number of sources, like 10 to the 8. This is just a few minutes, actually, to do. And you can start to reconstruct the solution to your initial integral differential equation that was in principle not very simple to solve. So this is very stupid, but it works. Another more method that makes sense is to actually try to do some clever tricks. So we saw that we can use maybe scaling units. So basically space and time are related. So I can, instead of having partial differential equation, I just have ordinary derivatives. And it makes, and you can use some techniques basically to solve it. And actually you see that the two methods agree quite well. So it's nice that you have two complementary methods to do that. And what's nice is that one is stupid but parallelizable, and you don't have to assume anything. And it gives you very good numerical stability. And the other is kind of a neat solver, but still you are in principle, it's difficult to add, you need to assume scaling, and you need to make some assumptions to make it work. So the fact that the two work together is a good sign that you have something that makes sense. Okay, and now I reach my conclusion just in time. So I tried to give a short review on cosmic strings, starting from their formation to their signatures and how we look for them. And as you could see, and I did not develop this part because I wanted to keep the talk simple, there are some tensions and approximations in our current way to compute their predictions. So there is still room for research and also a need for people to look into it. And we opened this box that I kept hidden from you. There are some open problems. And one problem that I'm interested in is that there are hints that maybe fragmentation may play a role to get better predictions. And one of my projects right now is trying to build a model of fragmentation that makes sense and also numerical methods to solve it. And thank you for listening, and I'm open to questions.
Questions?
Thank you very much for a nice talk, and welcome to EIP, and for trying to explain to non-specialists as well. That's very much appreciated. So just a simple question. First of all, if I understand things correctly, are cosmic strings a natural consequence of inflation? And if that's the case, what will be the consequence if in the future experiments like LISA and so on, no cosmic strings are ever detected? Is there a consequence?
That's a good question. In my case, I'm not linking directly cosmic strings to inflation, but in principle you could. I looked at the paper again, sorry, it's one of my first slides, and it will break everything if I do that. But in the paper of Merisa Keleriadou, Genro, and Roche, they precisely look at models of grand unification theory that could explain inflation as well as other cosmological things. So if you look at this paper, you can see actual models that link everything together. And in all those models, I mean, most of those models, indeed, there were cosmic strings. Yeah. So in this paper below. So I guess if you want to explain inflation with grand unification theory, indeed, you would expect probably to have cosmic strings. But the question then is, when do they form? If they form early, I'm not sure they get so diluted that you cannot observe them. But actually, I've not not worked that much on this relationship. But yeah. Sorry.
Experiments, is that a problem?
It's a problem for me. No, it's fine. I mean, it's very interesting because topological defects, you have them like everywhere in physics. If you do condensed matter, so if we have like phase transition in the early universe, you do expect to see them. Then maybe they are not like caused by grand unified theories, in which case they may be lower energies, and maybe axion strings are, if you believe in axions, are maybe more likely. And in which case, I think their gravitational wave signatures is a bit lower. I'm not sure you can detect it, but then you still need to study cosmic strings to get axion predictions.
Thank you very much for the nice talk. Have you tried, because from the CMB, there is a stringent constraint on the contribution of cosmic strings. Therefore, have you tried to sort of add the constraint from CMB and constraint from LIGO to see what is the situation today or constraint, for instance, parameters of these models?
Sorry, I didn't get whether you said you are doing it or you were questioning. Yeah.
They are stringent constraint on contribution of cosmic strings in
the CMB. Yeah.
The CMB.
Yeah.
Try these two constraints together to see what we find if we can better constraint model as fragmentation of groups and functions.
Yeah, so that's a good question. So the easy answer is yes. So you see, for instance, those are the plots from the LIGO O3 paper, and we put like in dashed brown the CMB constraint. So in one case, basically, you see that they are kind of the same order as the stochastic background, actually, in one case. And I would say that they are also less prone to model dependence, because the CMB constraints, they are more dependent on the infinite string network. And I think we better understand the infinite string network than the loops, because loops, precisely, they have some fragmentation, they have some complicated thing. So I would be more prone to believe CMB constraint, actually. I'm not advocating for my field, but I mean, too bad. Now I'm permanent, I can say anything. But yeah. So there are, but if you think about PTA, you see then the line is much below. So the constraints you have from PTA are much better than the CMB in this case. Yeah, I've not worked precisely on the relationship with between inflation and cosmic strings. I mean, inflation also comes from, I mean, can be seen as a way to avoid cosmic strings because they would dilute the system. I mean, it's also one of with the monopoles problem as well. So yeah.
Okay, last question.
Very naive from people outside of the field. Thanks for the pedagogical introduction first. I was wondering more of a curiosity of the role of turbulence. Is it important? Does it play a role in the behavior of strings? Could it play a role in the fragmentation of strings? If it's a stupid question.
No, I'm thinking. So in principle, this is not a phase that I've worked on, but in principle, when you start forming the cosmic strings, there's a friction period where I think maybe you could have those types of effects. But the idea here is that we have some attractor solution. So eventually we lose basically this information afterwards. And then there's another idea that might be linked to turbulence, is the fact that when you have a cosmic strings that propagating through a medium, it can provoke wakes behind it. And I know that Robert Brandenberger and his group have worked a lot on those wakes. And probably you could have some turbulence effects in those wakes. But this I'm not an expert of. But that's a two-way I could see turbulence.
Okay, let's thanks again, Pierre, and congrats for